Hello and welcome to Grokking Graph Analytics and Algorithms. Today we're going to be talking about breadth first search. Breadth first search is the second of two major search algorithms. Recall that depth first search is quick to implement but has some flaws in how it chooses to explore a graph. As an alternative, we can consider breadth first search. Let's consider the following problem. Say the latest polka band is in town and you just have to see them. Tickets are sold out, but you think your friends might have tickets. So you make a list of friends and plan to go to each one asking if they have a ticket. But you know none of them are huge polka heads, so you'll cross each one out as you go. But once you ask one of them, you'll also get a list of their friends, just in case they happen to be huge polka heads. So you plan to go see your friend Alice and ask if they've got any tickets. As a backup, you'll go to your friend Bob, and then you'll go to your friend Claire. Well, if Alice doesn't have any tickets, you'll ask for a list of her friends, and so you'll add Dan and you'll add Ellen to your list. And if Bob doesn't have any tickets, you'll ask for a list of his friends, and you'll add that to your list as well. And then if Claire doesn't have any tickets, you'll ask for a list of Claire's friends and add that to your list. Now that you've exhausted asking all of your immediate friends, you'll go to your second level friends, and you'll continue this until you find a ticket. Let's try to model this as a graph problem. What do you think the nodes and edges should be for this? Alternatively, ask, what are our entities and what are our relationships? Go ahead and pause the video and consider for a moment. For connections between people, it makes sense to define the relationships between them as the edges. And then, for the nodes, we can use the actual people. So let's try to visualize this search for polka tickets as a graph problem. Here are our first level friends, Alice, Bob, and Claire. And here's all of our friends' friends, Dan, Ellen, Frank, Gwen, and Horatio. And here, I've drawn in lines representing the relationships between people. So here's our friendship graph. We have individual people represented as nodes, and we have their relationships represented as edges. You might notice a few things. For example, Alice and Bob are friends, and Bob and Alice are both friends with Ellen. Also, Ellen is friends with Frank. These relationships will come up in our search, but let's go ahead and start with our original list. So to initialize the search, we remind ourselves that we're going to ask Alice, then Bob, and then Claire. So let's go ahead and ask Alice. Well, Alice doesn't have the ticket, so we cross her off our list, and then we get a list of her friends. Well, we notice Alice is friends with Dan, Ellen, and with Bob, so we write all of them on our list. Then we ask Bob. Bob doesn't have a ticket either, so we cross him off our list and get a list of his friends. And we see that Bob is friends with Ellen, Frank, Gwen, and Claire. Ooh, he is a popular fella. So we add Ellen to our list again. We also add Frank, and we add Gwen and Claire. And Bob and Alice are friends too, so we have to add Alice to our list. And then we ask Claire if she has tickets. She doesn't, so we cross her off our list and get a list of her friends. Pause the video for a minute and try to guess who we're going to add to the list next. Okay. Once we've asked Claire for tickets and found out that she doesn't have a spare ticket, we have to add all of her friends. The Claire node has an edge connecting Horatio, so we add him to the list, but Claire is also connected to Bob, so we have to add Bob back to the list as well. Our next step is to ask Dan. He doesn't have tickets either, so we cross him off our list and get a list of his friends. Dan is only friends with Alice, so we'll add Alice to our list. Now we're at Ellen. Let's say Ellen doesn't have a ticket either, so we cross her off our list and we add her friends too. That's Alice again, and then Bob, and Frank. Now we're back at Bob, but we've already asked Bob if he has tickets. It would be a waste of time to ask him again, so we actually just cross him off our list without adding him because we've already added him and asked him if he had tickets earlier. We then just continue to ask the rest of the people in our list. But we've already asked Ellen, so we can cross Ellen off our list without visiting her. The next person we can ask is Frank. Let's say Frank doesn't have the tickets. Who do you think we should add to our list now? Go ahead and pause the video and think. Since Frank doesn't have tickets, we add the people he's connected to. That would be Ellen and Bob. Keep in mind, we've already asked Ellen and Bob for tickets, so once we visit them, or once we get to those points in our search, we're actually just going to skip over them again. So the next person we ask is Gwen. Let's say Gwen has the tickets. At that point, we can conclude our search, and we can put a little exclamation point next to Gwen to remind ourselves that she has the ticket and to send her a nice edible arrangement. So that's breadth first search in a nutshell. The cool thing about breadth first search is that it finds the shortest path. That's because we start the search on sort of a frontier with the nodes that are closest. And then, at the next level, we check the nodes that are neighbors to the nearest nodes. And then we continue that way by checking our neighbors' neighbors and our neighbors' neighbors' neighbors until we exhaust the search. Let's revisit our search list. When we built this list, we added people in the following order: Alice, then Bob, then Claire, then Dan, then Ellen, and Bob again, and so on. And the order in which you were added to the list was the same as the order that you were searched in. This is what's known as first in, first out. And a great data structure for implementing first in, first out algorithms is a queue. Whenever you hear first in, first out, you should consider using a queue data structure. This is essentially a list that you can append on the end and pop elements off at the beginning. Let's look through some pseudocode for breadth first search. Let's go ahead and implement a breadth first search algorithm in pseudocode. For our input, we'll need a graph, G, and we'll need a root node that we can start at. We'll call that R. Well, breadth first search uses a queue, so let's go ahead and create a queue variable. Call it Q. And we also want to add our root node to that queue. You'll notice that instead of just saying push like we would in a stack, I'm saying push top. That's because a queue is double-ended. We put stuff in at the top, but we take things out from the bottom. So it's important to keep that in mind whenever we're implementing queues or describing algorithms that use queues. Our next step is to just perform a while loop as long as we have elements in queue. So, as long as queue is not empty, we're going to continue the following code. We're going to pop an element off the bottom of queue. If the element is equal to our search target, then we're done. Otherwise, we want to mark the element as visited. Then we want to go through each of the element's neighbors. If the element has already been visited, we don't need to visit it again, so we're not going to add it to our queue. So we check if the node hasn't been visited, and if so, we add it to the top of our queue. And then we'll continue this loop as long as we have unvisited neighbors. If we check all of the nodes in the graph, then we'll end up with an empty queue and we'll break out of this loop. But we haven't found the element that we're looking for, so we're going to return some kind of failure state. And that's breadth first search in a nutshell. Breadth first search is a really useful search algorithm for looking for an element in a graph. One thing to note is that it finds the path to that element in as few jumps as possible. That's because it uses an expanding search frontier. But you'll notice that the graph we've looked at is unweighted. If you have a graph with weighted edges, that is, if certain searches are more expensive than others, breadth first search will find the path with the fewest jumps. This might not be the cheapest path. For that, we need to use Dijkstra's algorithm, which we'll look at in the next section. Thanks for watching, and I'll see you there.